Thank you. Our next presenter is Dr. Xiaomeng Li. Xiaomeng is Dr. Li actually is a colleague of me here at QUT, and she is a research fellow and slash the assistant, which is equivalent to the assistant professor in research in the US setting at the Center for Accident Research and Road Safety, Queensland, CARSQ, here at QUT. And Dr. Lee's research interests include road traffic safety, driving performance, and ITS and traffic engineering. And today, Dr. Lee will be talking about exploring drivers' mental workload and visual demand while using in-vehicle HMI, which I believe human-machine interface for eco-safe driving.
Okay. Thank you very much, Professor Xiaomeng, for your introduction. Hello, everyone. My name is Xiaomeng Li. I'm from CARSQ, Queensland University of Technology. I'm very glad to have this great opportunity to share my research that we published on the special issue of AAP. So the topic I'm going to present today is exploring drivers' mental workload and visual demand while using an in-vehicle HMI system. Before I start, I would like to acknowledge the co-authors of this paper, who are Dr. Ati Vesiper, Professor Andrei Raktonirani, Dr. Sebastian Demo, and Dr. Oscar Avido Trespalacios. And this research was funded by the Australian Research Council Discovery Project. So first question, what is eco-safe driving? I think for most people, they are more familiar with the term eco-driving. Eco-driving is a driving style that has been advocated for decades that improve the environmental sustainability by reducing the fuel consumption and the traffic emissions. So in this research, we promote eco-safe driving. Eco-safe driving emphasizes the integration of both eco-driving and safe driving behaviors. And then the second question, why do we need eco-safe driving? So in addition to the reduction in fuel consumption that totally belongs to the eco-driving part, the eco-safe driving also promotes behaviors that related to smooth acceleration or deceleration, also reduced speeding time and safe car following distance. And more specifically, our previous experimental research has shown that eco-safe driving can lead to a 6.7 reduction in the fuel consumption and 33% percentage increase rate in smooth acceleration behavior, and also 25% increase rate in smooth deceleration behavior, and also 50% reduction in the speeding time, and a 16.7% increase in the car falling headway. So to summarize, the eco-safe driving is beneficial for both the environmental sustainability and for road safety. And the last question is, what are our concerns in this study? So thanks to the development in the V2V and V2I technologies, they provide essential information and technology support for designing the in-vehicle HMIs to support the drivers in eco-safe driving behaviors. But the problem is that those in-vehicle HMIs, they introduce additional information to guide the drivers to adjust their behaviors. And this may lead to an increased risks of an overwhelming mental or visual workload, and then further degraded the driver's acceptance or usability of those technologies. And most previous research, they have mainly focused on evaluating how those HMI systems have improved the driver's behavior performance but somehow they overlook the importance of evaluating the driver's mental or visual workload while using these technologies. And this lead to the aims of this study. So in this study, we want to compare the driver's mental workload when different types of eco-safe driving information are conveyed. And secondly, we want to explore the allocation of drivers' visual demands in different road situations. And thirdly, we want to verify the consistency of the workload patterns measured by the eye movement data and also the questionnaire data, which is the NASA TLX mental workload questionnaire. And our hypotheses are that firstly, drivers' mental workload increases as the amount of information conveyed to them increases. And the second one is when using the HMI, drivers experience a higher visual demand and workload at more complex road situations. And the last one is the change tendency of workload indicated by the eye movement measures should be consistent with the subjective measure. Methodology, firstly, designing an HMI system. So to ensure the usability and the acceptance of an HMI system, we applied an iterative human-centered design approach. And a series of focus groups and expert workshops were conducted for the development of the HMI prototype. And we also use the technology acceptance model as a theoretical framework to guide the design of the HMI. And the final HMI prototype composed of an Android smartphone as the display interface. And the interface was mounted in the front middle of the vehicle. And also an eco-safe driving algorithm was designed and inserted into the HMI to determine the release of the eco-safe driving information based on the driver's real-time driving performance. So for the HMI system, we designed 3 types of eco-safe driving information. And the first type is the advice information. This information was designed by a yellow background with some simple icons of the brake pedal and the gas pedal. And this information was conveyed to the drivers when they approached specific traffic events, such as when they approach the intersections or when they approach a front leading vehicle. And the second type of the HMI information is the feedback information. And this was designed by some cartoon faces with emotions. And this information was provided to drivers when they complete a deceleration or acceleration action. And the emotion of the face was dependent on whether the acceleration or deceleration was performed in an appropriate or inappropriate way. And the last type of information was the advice and the feedback information. So this is a continuous information that is provided to the driver when they approach specific traffic events and when they complete a deceleration or acceleration action. And the equipment we used in this research included the CASQ high fidelity driving simulator and the FaceLab eye tracking system. The simulator we used has a 6 degree of freedom and a full-size cabin, providing the drivers 180 field of view. And it also has a real operational interface with the environmental noise and the vibration system. And the FaceLab eye tracking system used a set of cameras installed in the vehicle to record the driver's head and eye movements in real time. So for the experiment, we designed a complete full circle driving road to test the HMI. The driving road consisted of a series of traffic events, such as the intersections, pedestrian crossing, and carpooling. But in this study, we only focused on 2 scenarios. One scenario is the stop sign intersection with the crossing traffic, and the other scenario is the stop sign intersection without crossing traffic. So drivers need to come to a complete stop at both intersections, but the complexity of these two intersections is different, with scenario 1 higher than scenario 2. Participants. We recruited a total of 53 participants, but due to motion sickness and some issues related to the eye tracking system, we only collected 36 participants with complete data. And those participants were half males and half females. And they were, their age was from 18 to 65 years old, with an average of 31.4 years old. And our requirement for the recruitment is that all the participants need to hold a valid driver's license in Australia. As the normal procedures of a driving simulation experiment, the participants need to sign a consent form after their arrival. And they need to complete a familiarization drive to get used to the operation of the simulator and also for the motion sickness check. And then we explain the participants with the use of the EcoSafe HMI system. And after that, participants completed 4 drives on the same driving road corresponding to the 4 HMI conditions. The 4 HMI conditions are a baseline driving without any HMI information, and the voice only information condition, feedback only information condition, and also condition with both the voice and the feedback information. And these 4 drives were completed in a counterbalanced order. And after completing the 4 drives, the participants completed the mental workload questionnaire, and then they were provided 70 Australian dollars as a reward of their participation. So during the experiment, we collected 3 types of data: the behavior data, the eye movement data, and the questionnaire data. For the behavior data, we analyzed the maximum brake force and the brake force standard deviation when the drivers approach the intersection, and also the average acceleration when they left the intersection. And the eye movement data included the total blink time, the average blink duration, the blink frequency, and the pupil size. So these are all the commonly used variables that measures an objective mental or visual workload. And the questionnaire data is the NASA TLRX workload survey. Results. So let's have a look at the driver's behavior performance between different HMI conditions. For the brake behaviors, we found that drivers had a lower maximum brake force and a lower brake force standard deviation in the AF condition, which is the condition that provided both advice and feedback information compared to the other conditions. But this difference was only observed in scenario 1, which is the complex intersection with crossing traffic. For the acceleration behavior, we found that the average acceleration when driver left an intersection was reduced in the conditions with HMI compared to the baseline condition. And this difference was significant for both scenario 1 and scenario 2. For the visual performance, we found that the driver's total blink time was longer in conditions when they were using the HMI compared to the baseline condition. And this difference was also significant for both scenarios. Similarly, for the blink frequency, we found that driver's blink frequency was higher in the conditions with HMI, especially for the AF condition compared to the baseline condition. And this difference was also observed for both scenarios. And let's have a look at the driver's visual performance between different traffic conditions. which is the comparison between scenario 1 and scenario 2. So when the drivers were using the HMI system, their blink-related variables, including the total blink time, the average blink duration, the blink frequency, they were all smaller in scenario 1, which is the more complex scenario with the crossing traffic than the scenario 2. In contrast, the driver's pupil size was larger in scenario 1 than scenario 2. And the last part of the results is the subjective workload, which was measured by the NASA TLX workload questionnaire. And we found that the driver's self-rated workload was higher in the AF and FO conditions compared to the AO and baseline conditions. And this result was consistent with the result that is indicated by the blink variables. So what did the results tell us? Firstly, we identified the effectiveness of the HMI in promoting the eco-safe driving behaviors. So when the drivers were provided with both advice and feedback informations, we found that those drivers tended to apply smoother and more stable brake control behaviors, especially in the complex intersections with crossing traffic. And also we found that at both intersections, drivers tended to apply a smaller acceleration when they left the intersection while using the HMI. And secondly, we evaluated the driver's mental workload differences related to different HMI conditions. And our findings show that the objective and subjective measures of the driver's mental workload show consistent patterns. And also we found that drivers experienced a higher mental workload when they were using the HMI. But the higher mental workload was still in a reasonable range. And this was concluded by the mental workload score in our study by comparing the mental workload score in the previous relevant studies that tested driver assistant systems using the same questionnaire. And moreover, we found that an increased driver mental workload was related to more active blinks activities of the participants. But an increase in the driver's visual demand was related to blink inhibition. So this opposite tendency in the driver's blink activities was reflected by the changes in mental workload and visual workload, respectively. So implications from this study. So from these research findings, we found that the blink-related variables are more valid measures of drivers' mental and visual workload. For the pupil size, it is more challenging to differentiate the changes in the pupil size caused by mental or visual workload. And in terms of the HMI design, we think that using the intuitive icons is better than using the pure text or pure numbers. And this is the maybe the reasons that we found a lower workload score in this study compared to the previous relevant studies. And lastly, we think that the eco-safe driving style is feasible with the assist of HMI, but we need the validation studies from the real-world driving tests. So that's all my presentation. Thank you for your attention. Thanks.
Thank you, Dr. Lee. That's a nice and interesting presentation. I can see that already we have received a comment plus question. So Cheng Hu has commented that thank you for your wonderful presentation. And Cheng's question is that HMI interface is so cute that I can't help watching it, such a comment. So, and his follow-up question is an interesting one. Will it cause more distractions in driving?
Yeah, actually, this is a very good question. And a distraction related to the use of a vehicle HMI is really a very important issue that should be considered when designing the vehicles or the driver support systems. And actually, we have evaluated these problems by using the driver's eye movement data, especially by using the driver's gaze data and their saccade distribution between the traffic road situation and their gaze distribution on the HMI system. And this result has been published in a paper on transportation research part F. And our finding is that our HMI system didn't cause driver distraction, and it lead to more gaze attention on the front road when the drivers are using the HMI system. So this also highlights that when you design and evaluate in-vehicle HMI system, you really need to have a fully comprehensive evaluation from the behavioral part, from the user experience, from their mental workload, from their visual workload, yeah, from all the parts. Yeah.
Okay, thank you, Dr. Lee. And I have received another question from the conference chair, Professor Xiaomeng Lee, and his comment was that it looks like that a considerable number of participants suffered from the simulator sickness for your experiment. And could you please comment on that? What type of participants they were that suffer from motion sickness, or did it happen for anything in the experiment design? And is there any way to minimize those simulator sickness?
Okay, let me have a check the number of participants that was excluded by motion sickness in our study. So we recruited 53 participants in total, and 15 participants were excluded because of the motion sickness. And I have to say that is a very common issues that we experience when we perform a driving simulation experiment. And I think that those participants that experience severe motion sickness symptoms should be really excluded from the data, especially from the start of the experiment. That's why we perform a familiarization drive for all the participants. And then after the test drive, we asked a questionnaire that evaluate their different levels of motion sickness. And for those participants that have very severe symptoms, we would suggest them to stop the experiment from that moment and avoid any discomfort from the further experiment. Yeah, I think that's a very natural issue in the simulation experiment, but we have some approach that could exclude this interference from the beginning. Yeah.
Okay, thank you, Dr. Lee, for the nice presentations and exciting talk. So I will now move to the next presenter. And so, Dr. Lee, could you please turn off your camera and stop sharing the screen?